Class, today we are going to be talking about the solar system. I will be focused on how to determine the battery bank size and select the inverter, plus the number of panels, the solar panel that we need. However, before I move on, I need to make a correction. I made a mistake on the previous video on this math, basic math. My apologies because of that. Because 6.1 times 3.3, which is the factor that this inverter has, this factor is telling you the number of times that the unit of energy that the inverter gets at the input is multiplied by this factor, and that is the unit of energy that we have at the output. In this case, it has to be 20.13. And then multiplying this times the number of hours of autonomy that I want, 2 hours per day, 40.23 ampere per hour. Ampere times hours. And for 3 days. So I want that my bank be able to satisfy my needs during 3 nights, 3 days, okay, with this ampere per hour, for a total of 120.78 ampere per hour per day. Okay, there is another aspect that I need to mention here. So this is a dwelling unit, typical dwelling unit in Southern California. This is the total volt ampere. That there is an extra video that you can go over load calculation. Okay, this is the total volt ampere per a dwelling unit whose square footage is around 3,200 square feet. So you could find this video, extra video, okay, together with these solar panel videos. So if I divide it by the number of hours that the solar panel can get maximum energy in the Southern California, which is 6, and Arizona. So I divide this. So my solar panel, it doesn't matter if they are exposed 14 hours or 16 hours. In reality, they are able to capture the maximum energy per 6 hours per day. So per day, my panel will be capturing 4,127.8 volt ampere or watts. I can interchange volt ampere and watts if I am dealing with a dwelling unit, house or apartment. If it is an industrial site or commercial site in which you have a lot of electrical motor or some kind of lighting system that use transformer, I cannot interchange volt ampere with watts. But in this case, this is equivalent to what? 4,000 watts. The question is, how many panels do I need? The answer is, depending. So this panel, each of these panels is able to produce 300 watts. Okay, so I divide 4,000 by 300 watts. So if I divide 4,000 volt ampere or watt by 300 watts, randomly, it will be giving me 14 panels. So 14 panels will be able to produce this amount of energy during 6 hours. Are you follow me on this? I hope so. Okay. And the other aspect is, this is the number of panels. How many batteries do I need for 3 days of autonomy? I divide the total ampere per hour per day by the voltage that each battery is producing me, which is 12. These batteries are able to produce 12 volts. 12 volts. That is the reason I connect 3 of them in a series circuit for a total of 26 volts. Okay, and if I need 120 ampere per hour per day by 12 volts that each battery is giving me. I need 10 batteries. With 10 batteries, I will be able to supply this energy during 2 days, and each day 3 days, and each day 2 hours. If I want to supply energy for more hours, I need to do this calculation, replace the number of hours here, 3 or 4, okay, and this amount will be increased, and as a consequence, I will need more batteries. Okay, so going back to the electrical installation right here. Okay, so we have, as I told you in the previous video, they are connected in a series. Why? Because the inverter works with 36 volts. If I have less than 36 volts, it won't boot up. The inverter will not start up. So I need 36 volts. Okay, and with 36 volts DC, 36 volt DC, if I check, the red one is the positive, the black one is the negative, I have 38.2 volts DC. So the output will be, because the factor is 3, it will be, I turn it on, and you can read here. The display is telling you the input, which is DC, and the output, which is AC. So 37.3 volts DC are converted into 122 volts AC. So I will check the output. My black one is the neutral, the red one is the hot, and I have here 120 volts. The yellow one here is my ground. So if I check here in my disconnect, so I am getting, after the fuse, I am getting nothing because it's open. I need to close this. Got it? I am getting here 120 volts. What is the size or rating of my fuse? It will depend. Divide this 3,000 watts by 120 volts. So that will be giving you the rating of your fuse. We need to use fuse to protect the output. Also, okay, right here will be the fuse size will be fuse rating AC 3,000 watts divided by 120 volts AC. I don't have a calculator, but it should be around 25 amperes, which is the size, the rating of the fuse that I have here. It's important because other than that, you have a short circuit. Okay, it's cheaper to replace a fuse than replace the whole inverter. Okay. It's 25 amperes. 25 amperes. Okay, so if you look at this, all of these fuses 25 amperes AC. Okay. So let me 25 amperes. And I disconnect this. But there is something missing here to have a safety system, protection before the inverter, to protect the inverter at the input. So I need here DC fuses, okay, DC. So this will be the side for my fuses at the input, okay. So I will install here a DC fuses. Where? On the red one. the positive. The negative goes directly to the inverter. So 10 ampere fuse at the input, because they are producing 20 amperes. So. Okay, that's it, guys. That is what I have for today. Okay.